These are the answers to homework 2G. Here are the definitions I would like you to know. Now let's go to the questions. Number 1, calculate the binding energy per nucleon for the following nuclear species. The first one is chlorine 37, and its experimental atomic mass is given. First, calculating the theoretical mass of a chlorine 37 atom. There are 17 protons and electrons. That would have a mass of 17.133025 AMUs. 37 minus 17 gives us 20 neutrons. So the mass of the 20 neutrons would be 20.173300. Adding this up, the theoretical mass of the atom would be 37.306325 AMUs. To calculate the mass deficit, we subtract this with the mass of the experimentally determined atom, and the mass deficit turns out to be 0.34042. This is the mass deficit. To calculate how much energy this mass deficit has been converted into, we take the mass deficit multiplied by the energy mass conversion factor of 931.5 MeVs per AMU. And then to get the binding energy per nucleon, we divide this by the number of nucleons in the chlorine 37 atom, which is 37 nucleons. And that gives us a binding energy per nucleon of 8.570 MeVs per nucleon. B, for the lead-208 atom, down the same way, calculate the theoretical mass of a lead-208 atom, subtract the theoretical and actual masses to get the mass deficit, convert it into energy units, divide it by the number of nucleons, which should be 208, and the answer should have come out 7.868 MeVs per nucleon. Number 2, radioactive sodium with a half-life of 14.8 hours is injected into an animal as a tracer experiment. How many days will it take for the radioactivity to fall to 10% of its original intensity? So after some time length, if its original intensity is going to be dropped down to 10%, that's going to be the value for N, and not the original amount can be taken to be 100. So if we use our equation for radioactive decay, and we want to solve this for how many days it will take for the radioactivity to fall to 10%, we're solving for the decay time T. So divide both sides by N naught, take the natural log of both sides of the equation, and then isolate T on the right side of the equation, and we now have an expression to calculate the decay time T. The half-life is 14.8 hours. The N naught value of 100 goes in the denominator, the N value of 10% goes in the numerator, and divide it by negative natural log of 2. If you switch that to positive natural log of 2 on the bottom, that means in the numerator, the natural log term would be N naught over N. You would have 100 over 10. Either way would be correct. This turns out to be a decay time of 49.2 hours. And if they want the answer in days, we'll have to just convert the hours into days by using a little conversion. 1 day equals 24 hours. So that means it would take 2.05 days to have the intensity of the radioactivity drop down from 100% to 10%. Number 3, if 1.000 grams of molybdenum-99 decays by beta minus emission to 0.125 grams in 200 hours, what is the half-life of the molybdenum-99? So once again, using the decay equation, in this case, we're going to be solving for the half-life, which is T sub 1/2. So once again, we'll divide by N naught. We'll take the natural log of each side of the equation. And now to isolate the half-life, we're going to bring that to the left side of the equation and bring the natural log of N over N naught to the bottom on the right side. So the half-life will equal negative natural log of 2 times T over natural log of N over N naught. If you want to use the equation without a negative sign in there, you can take the negative sign out. And in the denominator, you flip the N naught and N around. Plugging in the numbers we know, the decay time they told us was 200 hours. The initial mass of the radioactive isotope was 1 gram, that goes in the denominator. And after the decay time, its mass is 0.125 grams. And so solving for this, we're going to get our half-life in hours of 66.7 hours as the half-life for the molybdenum-99. Number 4, a sample of a radioisotope shows an activity of 100 disintegrations per minute. After 1 hour, the activity decreases to 77 disintegrations per minute. Determine the half-life of the radioisotope. So in problem number 4, we're solving for the same variable we did in number 3, so I'm not going to do the algebra again to convert the decay equation into solving for the half-life. We're just going to start with that equation. And in this case, the disintegration rates, which is what you get from a Geiger counter, can be used in place of N and N naught because they're proportional to the number of radioisotopes present. So it says initially it's 100 disintegrations per minute, that's going to be N naught. After 1 hour, it's down to 77 disintegrations per minute, that's going to be the value for N. So the decay time, 1.0 hours. The initial count from a Geiger counter, 100 disintegrations per minute. And then at time T, you'll have N amount of disintegrations per minute, which is 77. This gives you a half-life in hours, and this comes out 2.7 hours for this radioisotope. Number 5, a sample of wood from an Egyptian mummy case gives 9.6 counts per minute per gram of carbon. How old is the mummy case? This is done by carbon dating. We're going to be solving for the decay time, which in the decay equation is going to wind up being T. So to solve this for T, divide both sides by N naught, take the natural log of both sides of the equation, and we'll isolate the decay time T on the right side by dividing both sides by negative ln of 2 over half-life. This will be our decay time. The half-life for radioactive carbon-14 can be looked up. The N naught value, the amount of disintegrations per minute per gram of radioactive carbon-14 in living organisms, can be looked up, 15.3 counts per minute per gram. And the N value is the decay rate right now at this time, which is 9.6. So the half-life, 5,730 years. The decay rate right now, 9.6 counts per minute per gram. The decay rate for living tissue, 15.3 counts per minute per gram, divided by negative natural log of 2. And the decay time is 3,900 years. Therefore, we would assume the mummy case has that same age. Number 6, in a sample of uranite ore from the Black Hills of South Dakota, the mass of lead-206 is 22.8% the mass of the uranium-238 present. Estimate the minimum age for the Earth from this information, assuming these rocks from the Black Hills of South Dakota were formed at the beginning of the Earth. So we're going to try to determine what the decay time is, how long has it been decaying away, so we're going to solve for T. The half-life is going to be for the radioisotope, which is uranium-238, 4.5 times 10 to the 9th years. We just need the values for N and N naught. So the half-life we know. The N naught value is the original mass of uranium-238, and we don't know how much there was at the beginning of the Earth when these rocks were formed. But we do know the mass of the uranium-238 now in this sample we're dealing with. We can assume that its sample right now is 100 grams, or we could say 100%. We can do it either way. So if we take the rock is some amount of uranium, some amount of lead. If we assume it's 100 grams now, then we can say how many grams of lead there are in the rock at this time. So we have to make up a number, and it's good to make up the number 100 because it said the mass of lead is 22.8% the mass of the uranium. So if you make the uranium 100, the mass of the lead must be 22.8 grams. So therefore, we will use 100 grams as the mass of the uranium-238 now. Going back in time, the whole thing was uranium. We know the top half was 100 grams of uranium. The bottom half, we don't know. So we have to figure out where the 22.8 grams of lead came from. What did it weigh when it was uranium? Because the uranium decayed into the lead. So if we take the 22.8 grams of lead-206 that's in the rock now, use the molar mass of this isotope of 206 grams per mole to convert it into moles, in the decay scheme from uranium eventually turning into lead over a period of 4.5 billion years, it's a 1-to-1 ratio. One lead atom eventually turns into one uranium atom eventually turns into one lead atom. So it's a 1-to-1 atom ratio, a 1-to-1 mole ratio. Put the lead-206 on the bottom to cancel out the units, and we now know how many moles of uranium there must have been originally. And using the molar mass of the uranium-238 isotope, which would be 238 grams per mole, we can calculate that that missing mass of uranium in the original rock must have weighed 26.3 grams. So if we add the 26.3 grams with the 100 grams that are still present, that means the rock must have originally had 126.34 grams of uranium in it at the beginning of its life. So if that's the mass of the uranium originally, we now know all the variables to plug into our decay equation at the very top. And if we do this, we can calculate how long the decay process has been going on. And that turns out to be 1.5 times 10 to the 9th billion years. We would estimate that as the age of the Earth if we thought that the rocks were formed at the beginning of the formation of our planet. Number 7, what is a breeder reactor? A breeder reactor is a nuclear reactor in which fissionable fuel is produced while the reactor is running. 8, define each of the following terms. First term, somatic damage, and somatic damage is defined as radioactive damage to an organism resulting in sickness or death. B, genetic damage. This is radioactive damage to the genetic material of an organism resulting in malfunctions in the offspring of the organism itself. Number 9, list the 4 factors that determine the biological effects of a particular source of radiation. And the things that determine the effect of the radiation on biological systems are first, what is the energy of the radiation? And the amount of energy the radiation possesses is measured in rads, which stands for radiation absorbed dose. Second factor is the penetrating ability of the radiation. That really is determined by whether the radioactivity is giving off gamma rays, beta rays, or alpha rays, or particles actually. And we know that gamma rays are way more penetrating than beta particles. Beta particles are way more penetrating than alpha particles. So in this case, gamma radiation, the most damaging to living organisms. Third is the ionization ability of the radiation, and this is actually in an inverse order. Alpha particles having the higher charge are able to ionize things they strike more easily, therefore changing the structure of molecules. And if there are molecules in biological systems are changed or destroyed, that causes a potential problem for the living organism. Then betas, and then gammas. And then finally, the chemical properties of the radiation. For example, if you have radioactive krypton or radioactive strontium, both which can be produced from nuclear reactors or nuclear bombs, the krypton is an inert gas. It's a noble gas, therefore it doesn't bond to anything inside of a human system, and you actually would just exhale it out and it would have minimal effect. Where strontium, being an alkali metal, would behave much like calcium and magnesium. That can be absorbed into the bones and into bodies, and therefore staying in the system a lot longer, causing more damage.